I think we can start our third part of our conference. We have another honor guest is already there online, Alessandro Knowles. He is an associated professor in nuclear materials at Royal Academy of Engineering. Also research fellow several places, but to be clear, is the School of Metallurgy Materials, University of Birmingham. The way how we met and we started to talk is long. I think I shortened it. Maybe it would be better to say more about his background. It's in different areas, different topics, different materials, including aluminium, metal, matrix composites, then also collaboration with the Rolls-Royce, with the Imperial College, work on titanium alloys. He has been awarded with many prizes and fellowship. Also, Sandy was working on the BCC titanium super alloys, where he got the doctoral prize fellowship. Another area where he was working in the material research was the Eurofusion, and there he was investigating nanostructured tungsten alloys for fusion. So, many things. I definitely cannot mention all of them. If you want to, please add something more or anything about you, what we shall know for today's presentation. You are very welcome. Please to introduce yourself more. I hope that I didn't mess up everything. I am very happy to see you finally, at least like this in person. And please. The floor is yours, and we are looking forward to your presentation. Thank you.
Fantastic. No, thank you very much for a kind introduction and for the invitation. Is the PowerPoint coming through full screen okay, and you can hear me okay?
Yeah, it's okay.
Good. Yeah, thank you very much for the introduction. Yeah, I'm very sorry not to be there in person. I was at CVR just a month ago, so I was very glad, and that was kind of initiated this connection to do the seminar today and this talk. But yeah, really amazed the stuff you guys have got there is really impressive facilities and research going on, and I'm sure lots of really good ideas and discussions that have happened during the day today, so I'm sorry to miss in person. Yeah, so I'm Sandy Knowles. So I lead a research group at University of Birmingham. We have now about 15 people working on novel materials for a range of energy applications. And specifically today, I'll talk about kind of two key topic areas for the research group. This idea of BCC superalloys. So I'll explain what on earth that is, as well as high entropy alloys that I think probably with other colleagues here have become quite a area of interest, both for fusion and for generation 4 fission, so for kind of high temperature reactors. I guess some of the other links with CVR has been this COMPASS program. So this is actually for concentrated solar power, so thermal solar, so high temperature, using a field full of mirrors to make a central receiver point very, very hot, so you can sort of get hot enough to melt steel. And this is another application where you need some of these advanced materials. So in Birmingham, we're working on the development of new high temperature chromium alloys in this COMPASS and EU Horizon 2020 program. And in CVR, linked into some of the particles work, and particularly on supercritical CO2. So there's a nice partnership already between Birmingham, CVR, and other colleagues. So today in this talk, I'm going to focus in and talk a bit around kind of some introduction and motivation for high temperature applications and why we might need some new materials. Talk about a bit some of the challenges and this kind of idea of using refractory metals or BCC superalloys, and then talk about kind of two research projects we did previously, but also continue in the group on tungsten BCC superalloys and high entropy alloys. So I don't know, I think there's still some aerospace research. I kind of saw at least a couple of colleagues when I was at CVR that are working in aerospace, and maybe other people in the audience have multiple application areas they work in. But when we're working on gas turbines, we're particularly interested in reducing fuel efficiency, and often that comes into improving the operating temperature of the engine. So higher operating temperatures give you improved thermodynamic efficiency. So the same motivations we have in next generation nuclear as well. If you want high temperature reactors, you get this improvement in thermodynamic efficiency. In the aerospace gas turbines, a lot of the thing limiting increasing the temperature is the materials capability. And so in aerospace, we work on what's called nickel-based superalloys. So nickel is the main material. And over time, these have been continuously improved. Every 10 years or so, we get about a 50 degrees C improvement in temperature, but it's becoming ever harder to realize. So we have this kind of initial, quite kind of linear progression improvement, but over the last couple of decades, it's been really hard to get much improvement in the nickel superalloy properties. And so kind of as a research group, when we're working on aerospace materials, one of our questions is, okay, well, what are we doing? Is it that we've just hit some physical limit? Is it that we're just getting some kind of iterative improvements? The more money we spend, we get a bit more improvement. Or are there some kind of fundamentally new materials we can consider that might give us a sort of step change in performance? And I think now we're kind of looking at going from kind of kerosene-based gas turbine engines to hydrogen gas turbine engines. Maybe this is the point when we start really looking at fundamentally new technologies. The same is kind of true in the fusion thing. So sorry, slightly busy slide, but I think many people have already know as much or more than myself in the audience. But one of the key things in fusion is we have what we've currently got in the UK, the Joint European Torus. We're now building in the south of France, ITER, which is then going to be net energy out. So hopefully by the end of this decade, we'll have proved fusion. And that means we now need to really demonstrate and make it a functioning power plant. And as we look towards demo, which might be 2050, or alternatively, we look at some of the private companies that are doing fusion. So Tokamak Energy in the UK or Commonwealth Fusion Systems out of MIT. These companies are looking at feasibility by 2030 and power by 2040. But regardless of which kind of reactor type and some of the kind of plasma physics and the reactor geometry considerations, which materials can function as a power plant under fusion kind of spectrum neutrons for 20 years. And that's really something which we don't know how our current suite of materials would perform in a fusion environment. We're doing everything we can to demonstrate them, but probably there's also going to be a need of some fusion optimized materials. So it's certainly kind of made for temperature requirements as well as radiation damage. And then the last application we kind of work in as a group is in then next generation fission. So some similar motivations on just thermodynamic efficiency, some improvements in kind of reactor conditions and sort of waste production. Something we're particularly interested in the group is the benefits you might have in some of these high temperature processes for hydrogen production. So if you start looking at reactor temperatures more in the kind of 800,000 degrees C, it opens up new thermochemical processing routes for hydrogen, which would be a very good way of making low carbon hydrogen. But again, regardless of which kind of reactor design we have, we're going to probably need some new materials because we spent decades of work optimizing and in subsequent decades developing the original fission nuclear materials for sort of 250 or 350 degrees C operation. In the UK, we have some reactors operating at 550 degrees C, but almost all of the generation 4 reactors are talking more towards 600 to 1,000 degrees C operation. And so we're probably going to need some new materials to withstand those conditions. So this kind of leads us into the, well, what's so hard about meeting the requirements of high temperatures? So one thing is we just need something that's not going to melt, but we probably need to go further. It needs to have the right mechanical strength. We need to think about creep. We need to think about damage tolerance. We might think about fatigue and the environmental resistance, so both corrosion, oxidation, but also radiation damage. And then also, can we really manufacture it at the scale that we need, as well as can it be done at adequate cost? So in this is one which is originally kind of benchmarked for nickel-based superalloys, more towards aerospace, which do pretty well on all of these kind of criteria. They're pretty expensive, but otherwise they're a pretty phenomenal material. And if we kind of go to a new materials class, so this might be something like silicon carbide composites, which are also considered for Gen 4. You get some benefit in strength and creep resistance, but maybe that's at the detriment of cost and processability. So whenever we're developing a new material, we kind of have to try and ideally balance out all of these different properties. So it's not just designing for a single parameter, we have to try and design for all of them at once. And we're really kind of trying to get novel materials that it's not a complete sacrifice. Maybe it gets a good benefit in strength, but you don't lose out in other parameters. So for us, we take a lot of inspiration. So I did my sort of PhD in aerospace materials and previously worked briefly at Rolls-Royce. So we take inspiration from aerospace and try and bring that into the nuclear sphere. So some people in the audience might be familiar, but I'll just give a brief introduction to what nickel-based superalloys are. So these are materials that have very exceptional high temperature strength and creep resistance, as well as oxidation resistance. And fundamentally, these are comprised of FCC nickel as a kind of matrix phase, and this intermetallic, so nickel 3 aluminium, which you have this kind of composite benefit almost, where you have a very high strength intermetallic phase and then a ductile matrix phase. And you get these kind of cuboidal bricks and mortars where the bright cubes are the intermetallic and the channels are this gamma prime. So you have a very high volume fraction of precipitates. And we can design these alloys, and we really kind of do that fundamentally instructed by phase diagrams. So I spend a lot of my time going into different phase diagrams and trying to understand how we can use them to design and control microstructures. So for a nickel-based superalloy, we can first process and manufacture at high temperatures, whereas single-phase FCC nickel. So that means we can do cast and wrought or kind of thermomechanical processing. And then we do a cooling and do an aging heat treatment at intermediate temperature, where we develop in this two-phase field, so two-phase between nickel FCC in purple on the right, and then nickel 3 aluminium, the intermetallic. So we then are in a two-phase field, so we get precipitation. So nickel superalloys are a very exceptionally good material, but getting improvements has become ever harder. And so if we really want to go to higher temperatures, and if we also want to go into nuclear environments where we have concerns about helium generation from nickel, or also kind of just radiation damage within the FCC matrix, we might consider some other options. So in the aerospace community, there's kind of been this shift trying to increase melting temperature. So that's the first proxy for high temperature performance, is just what is your melting point. That gives you an absolute upper limit. And there's been quite a lot of work with many research groups looking at changing from a nickel base to a cobalt base. So that gives you nearly 150 degrees C, potentially improved melting point, which could give you an extra 150 degrees C operation performance. So if you shift from nickel to cobalt, you can get some very similar microstructures, this kind of gamma prime microstructure, and you potentially get some gains. So there's lots of work, and I believe some commercial alloys now in these kind of cobalt systems. You could then maybe go a little bit more exotic if you choose other FCC metals. So you could go to things like a platinum-based superalloy, or an iridium superalloy, and you could probably build a jet engine out of them, but you might need quite deep pockets to be able to buy your platinum, and probably have an armed guards around your airfields to stop people breaking in to steal it. I think also you just come up to an availability. There's just physically not enough platinum that you could build jet engines out of platinum. But there are some application areas where you could consider them if they're high performance but small volume. So going there, then we've run out of FCC metals. We can't take a direct analogy to nickel-based superalloys, but we consider, well, what about some of the other high melting point metals? So we could go and particularly jump, rather than being FCC, we could have BCC. So we have all of what we call the BCC refractory metals, and particularly things like tungsten. So why not consider these high melting point metals? And we asked the question of, well, if this gamma prime microstructure is so effective, is there an analogy to consider a BCC based system, so a beta prime? And this is what's kind of kept me busy for, I guess, coming up to 10 years now or so, of working on this concept of BCC superalloys. We're really trying to take inspiration of gamma prime, but now that we've changed to a BCC base, we also need to change our intermetallic species. So we have our kind of BCC unit cell that people may be familiar with. So there's lots of different metals that we can have as our base BCC matrix. And then we can consider, well, what is a beta prime intermetallic? Well, the simplest one is what's called the B2 crystal structure, where the center atom is ordered and your corner atoms are different species. So things like titanium iron, or people maybe more commonly is around nickel aluminium. There was a huge amount of work on monolithic nickel aluminium, so nickel aluminides, through the 90s for aerospace applications. So there's many of these B2 or beta prime intermetallic species, but one of the real challenges is, if we try and do the same thing we had in nickel alloys, is we need this equilibria between BCC and the intermetallic. So we can ask which systems, is there kind of just a binary system that directly gives us this kind of beta-beta prime structure? One of the only ones really is technetium. So tantalum technetium, titanium technetium do have a two-phase field between BCC and the B2. But technetium, I guess probably Siva has more experience than most than, but technetium has no stable isotope, so it's not something we're going to be making engineering structures out of, but very interesting from a kind of scientific basis, or maybe for medical treatments and things like that. So the only one of a binary system that really works kind of towards a beta-beta prime structure is the titanium ion system. So this was what I spent a lot of my PhD researching, and we still have onward projects trying to understand that as a binary system, which you'd think iron metallurgy and titanium metallurgy, this would be quite a well-determined system, but actually people haven't mostly been interested just in the edges of the phase diagram and not this kind of region in the middle and quite what happens there. But what we found is that you can have an equilibria in high temperature titanium alloys, so beta titanium, which are used commercially. If you keep adding even more iron, at some point you get to the point where you form this titanium iron intermetallic. And so we've done kind of a number of bits of work looking at trying to use this binary as the base to create a beta-beta prime or a beta titanium BCC superalloy. So taking the titanium matrix and having precipitation of titanium ion, and you either get some spherical or lamellar precipitation structures. So we've done work looking at the strength and the formation of these kind of microstructures. So taking in the rest of the literature, we're not the only people to have pursued this kind of BCC superalloy concept. So there's other systems, but none that have really kind of reached commercial maturity. And hopefully there's a few different directions we could go in that maybe could get us there. One of the ones that's picked up quite a lot of interest internationally has been refractory high entropy superalloys. So this was kind of a review paper that was Perspectives paper just published last year or so, 2 years ago. And at some of the major conferences, you're now seeing quite a lot more people looking at these, what I would call kind of high entropy BCC superalloys. So you can get this kind of gamma prime cuboidal sort of structures. So certainly something that's kind of seeing widening appeal in the scientific literature. So we've been kind of applying this BCC superalloy concept to another system. So we previously worked on titanium alloys, and then, as I was mentioning, around this Eurofusion project we had on nanostructured tungsten. And during that, we wanted to have tungsten with precipitates. So we tried to see if can we apply this BCC superalloy concept. So we got the motivation of BCC as high melting point. Essentially, this beta prime could be a reinforcing phase, but we also have interest in terms of the interfaces towards radiation damage. Well, the challenges we had is that really that there wasn't very much prior study of this system. I guess that's probably what interested me in it. And one of the questions we had is there this kind of equilibria between BCC tungsten and titanium iron? And this would be, are BCC superalloys even possible? And so then the next question is, are they useful? And I guess we're still answering that question, but they're certainly possible. So in this kind of study, one of the things we were doing was making real alloys. So we have alloys which are going from tungsten rich with 20% atomic titanium and iron. So these kind of go across in increasing tungsten concentration. And what we see is we get kind of different phases depending on the composition of the alloy and different volume fraction phases. But predominantly we get the two things we were kind of initially interested in, which was this BCC tungsten, which will have some amount of titanium and iron dissolved within the BCC. And then we get this beta prime titanium iron phase in purple. What was kind of interesting and we kind of were aware of, but didn't know if we would see it, is that there's also a second or third phase of BCC, which is BCC titanium. So actually there's, as well as having this two-phase precipitability gap between having the beta prime, there's also a spinodal reaction as well. So you actually have a three-phase structure. So two BCC phases and then this beta prime titanium ion. In kind of using this, so this was principally just a phase equilibrium study to understand like actually what is the chemistry of the phases in the ternary system. But in having done it, we kind of were interested within the dendrites, so the tungsten rich phase, we could see that there was kind of a secondary feature within those dendrites. And one of the things was just porosity, but it didn't really seem to be consistent with that from the imaging. And the question was whether this is this beta prime microstructure we were really seeking. So in that we could zoom in and we can do TEM to validate both the chemistry and the crystallography to find that we do indeed have this beta-beta prime structure. And we could start to probe into the performance of the alloy. So whilst we've done this experimental work to use to determine the phase diagram, we can take that then into a CalFAD thermodynamic assessment. So the ultimate aim is to try and do more prediction on these alloys, but if you don't have an understood phase diagram, you can't use many of the current predictive tools. But we're trying to kind of develop that predictive capability. And we also then started looking at some mechanical behaviors. So in these ones, we're doing just hot compression, but up to 1,000 degrees Celsius. And so in that, we're seeing massive benefits over state-of-the-art nickel-based superalloys or tungsten as a direct analog. So there is an advantage to having this tungsten material as well as having the beta-beta prime microstructure. The secondary interest for us, as well as trying to get the kind of mechanical reinforcement, is also to create interfaces. So between beta and beta prime, you'll either get a coherent or semi-coherent interface, so some interfacial dislocations and interfacial strain, and potentially that could be hugely beneficial for irradiation damage. So there's a lot of work on the oxide dispersion strengthened materials, which is showing if you have sink strength, so high area density of interfaces, this can help reduce irradiation hardening. And so that hopefully can improve your irradiation damage tolerance. So we have a number of bits of work looking at creating nanostructured materials and understanding the irradiation performance. So particularly, I guess, like there's lots of very good irradiation facilities at CVR. In Birmingham, we're very fortunate to have our own cyclotrons, so we can do proton irradiations up to temperature, as well as we're getting upgrades for in situ corrosion and mechanical loading, including high temperature. And we've received, and I think by the end of the year, it will be operational, a neutron accelerator. So I think we can still get up to 0.1, maybe a bit more DPA. So we can kind of start to do some irradiation studies as well as neutronic studies. So this is kind of probably one of the higher energy accelerator high energy and damage levels for an accelerator system compared to if you go to a reactor-based systems where probably you can get some higher damage levels. But differences in terms of the energies involved as well. So I'll do a whistle-stop tour through also on high entropy alloys. So this has been an area which is seeing massive research in the community. So nickel-based superalloys, which are used in every single jet engine and fund many research groups internationally. There are now more papers published on high entropy alloys than nickel-based superalloys. So scientifically, they've become very interesting. I think there's a fair few patents out in this space, but I haven't yet seen one fully commercialized, but they are massively catching interest. And the idea in a high entropy alloy is this concept of, rather than having a single base element, so if we consider this kind of a ternary diagram, but it also extends into higher order compositions. So we first were talking about tungsten alloys. So okay, we take tungsten and we look at the middle, we kind of add a small amount of X and Y. We then look at steel metallurgy. We add, a few percentages of other elements. In a high entropy alloy, the idea is that you go really kind of and add different elements at equal parts. And originally the definition is that you have more than 5 different elements mixed in approximately equal atomic concentrations. And whether you get kind of anything interesting there. So the initial observation was Brian Cantor and Ye, who separately kind of came across this concept, mixing together, if I remember off the top of my head, cobalt, nickel, manganese, iron, chromium. And so these are elements that have, they're on the common row on the periodic table. But if you mix them together with the differences in crystal structure, you might anticipate that you would either get many crystal structures or you even would form intermetallic phases. But the unusual observation was that they got a single phase FCC material. And it had properties that were very different to any conventional alloy. And so this kind of idea has then caught a lot of interest in how we could discover and demonstrate new materials. So in high entropy alloys, there was this idea that it's because you're mixing lots of elements together that you're gaining an entropy, and hence the name. So maybe you get entropic stabilization. And there's a number of other benefits that seem to be maybe coming out of this, particularly towards high temperature strength and slow diffusion. And also one of the ones that catches a lot of my interest is that quite a number of high entropy alloys are showing a very good irradiation damage tolerance, potentially much better than conventional materials. So that's a very interesting concept for us to either to understand and also to exploit. The challenge with high entropy alloys is you can have any high entropy alloy, you can just mix any element you like and put them together. Maybe if you put 4 or 5 plus, that is a high entropy alloy, and that means we have almost an infinite number of possibilities of how many high entropy alloys we can make. So if we're going to choose a kind of new research study, we could potentially take a good starting point. So we've got the Cantor alloy, which we could look at and take that as a starting point. I quite like the joke one, we could play dartboard metallurgy and design kind of a different master's project or summer project, and we could just throw darts and pick elements. So we could do zirconium, vanadium, molybdenum, zinc, or something like that, and that could be a new high entropy alloy, but probably we need to be a bit more scientific than that. We can use things like CalFAD thermodynamic predictions, or maybe some other modeling methods. So all of these have challenges, particularly in CalFAD, as we were saying in the tungsten-based superalloys, is one of the challenges. If you don't have the prior data, you can't make a good prediction. So we've been kind of looking at some high throughput modeling screening methods. So put my hand up, I'm an experimentalist. I was working with Dan King and Simon Middleberg on this. They're the sort of modelers, and trying to use this. This was actually a data library approach, looking at atomic size misfit as well as then your propensity to form a solid solution. So your Gibbs free energy of mixing versus intermetallic formation. So we have these 2 parameters, kind of things with not very large atomic size misfit, as well as a low driving force for intermetallic production. And the nice thing was with this approach, which the code is kind of publicly available, we could screen, in this case, 100,000 compositions, and we've subsequently done another study where we've done over 1 million high entropy compositions. And we were interested in both those that might be a single phase solid solution, as well as ones which might have a low thermal neutron cross-section. So particularly we were interested in these as potential fuel-clad materials. So we came across this system, niobium, titanium, vanadium, zirconium, and noticing that of those 4 elements, zirconium is probably the lowest neutron cross-section. We then did the derivatives looking at changing the zirconium concentration to change the neutron cross-section. So having taken and defined these compositions in this system, we then did apply CalFAD to that to try to see how well it does the prediction. So this predicted that there does exist a single phase. So as we go down in temperature, first you're liquid, then you form solid BCC. There's a large temperature range in which BCC is stable, or at least the predictions say. And then at low temperatures, we might get some mixture of phases between lavas, spinodal, and HCP. So we then went and produced these alloys experimentally. So one of the things that is a caution in many high entropy alloys is how they're produced. So are they often they're formed with very high cooling rates, and one of the questions is, are they truly stable? So for us, that as we're kind of wanting to use these materials in a nuclear reactor, they're going to sit at a high temperature for a long time. So they do need to be temperature stable. So in this system, we did find that these niobium, titanium, vanadium, zirconium high entropy alloys are single phase stable at 1200. So they do kind of meet this criteria of being a high entropy alloy. So there is potentially some entropic stabilization involved. However, what we found is wanting to kind of go towards maybe reactor operating temperatures. At 700 degrees C, you get then precipitation and forming second or third phases. So depending on the composition, the zirconium concentration, we got differences in microstructure. So we got some spinodal, we got some HCP formation, as well as lavas phase formation. So we went in more detail to work out, okay, well, exactly which phase is which. So going into TEM, doing composition and linking that to the XRD and diffraction to identify the phases. And then we went on to then compare just the base mechanical behavior. So this was very preliminary studies where we're just looking at hardness. So these things are about twice as hard or twice as strong as zirconium and steel is currently used. So you might be able to make an argument if you can make things a bit stronger, you can also make them maybe a bit thinner. So maybe there's some advantages to be had there. In this thing, the fact that we have multiple phases is for us maybe not a problem. We're also interested in high entropy alloys that have precipitates. In the same way we had the nanostructures tungsten, why not have nanostructured high entropy alloys? So we could use these second phases for improvements in mechanical strength and high temperature strength, as well as for irradiation damage resistance. So we have a number of different projects. So we've just had 2 PhD student starts. We've got 2 postdoctoral research fellows working kind of in this area. So particularly around can we control and optimize the phases and get the best optimum balance of mechanical versus irradiation performance. We also have interest towards fusion of reduced activation high entropy alloys. So in these ones, if we have certain elements for fusion become very active, and they would mean that your entire fusion reactor becomes long-lived radioactive waste, which kind of defeats some of the initial motivation for fusion. So we're looking at ones that would kind of meet the criteria of ideally becoming low-level or low-activity waste after just 100 years. So it includes, we've been exploring these concepts of BCC superalloys and high-entropy alloys, particularly looking at phase diagrams to instruct the design. Generally, we're finding that they are possible and interesting, and they demonstrate high strength. But there's some challenges certainly in ductility in many of the BCC, particularly tungsten-type BCC metals. So we have a lot of work focused on designing for toughness and microstructure design, as well as then linking that into irradiation and then environmental resistance. So yeah, some big thanks to the team at Birmingham who have been working in on this, so a mixture of postdocs and PhD students, many funders who are involved supporting this work, and then I'll just leave that on screen, which is kind of a summary of some of the stuff we're working on as a group. So yeah, happy to take any questions.
Thank you, Sandy, for extremely interesting presentation on another set of materials, which are, as you said, now largely researched, high entropy alloys. So is there any question? Yeah. I would say it's because it's after lunch, you know, but our audience is a little bit shy. I know that you have been lately in CVR, and you are also working on COMPASS with our colleague dealing with materials for supercritical CO2. So we have really a large portfolio. So just curiosity, did you come to some common ground that our collaboration will continue or might continue also in the direction, for example, the high entropy alloys? So
yeah, very, very keen to. I think the fact that you guys can do real reactor stuff is so we've kind of got this interest in terms of the radiation performance, but depending on which ions you irradiate with and what performance you get, there's a lot of work to do. So yeah, I think the supercritical CO2 in this high entropy alloy and BCC superalloy concept, many in both fusion and in some of the generation 4 fission designs, we're equally interested in the supercritical CO2. So I think whilst we start off this project on the COMPASS on chromium alloys for thermal solar, it very much extends into what we can do on high entropy alloys and BCC superalloys.
Okay, it's very nice to hear that, and definitely we are glad that you gave us your presentation today, and we can maybe see you next time again. And thank you very much for your presentation again. If there are no questions, yeah.
Thank you, John. A pleasure. I look forward to visiting again, and yeah, feel free if anyone wants to either get my email to ask any questions. Very happy to be in touch.
Okay, so you can of course stay with us, and we can go on with our program. So
thank you.
Then, okay, thank you. Yeah, very long title of the presentation. I already did. Latest trends in nuclear component manufacturing with a focus on small modular light water reactor design.
Yes, right.
Thank you.
So, good afternoon, ladies and gentlemen. My name is Strecius, and I have been working for CVR since 2011. And in my speech, I will be speaking about production of thick wall components suitable for nuclear industry. The nuclear industry stands at a very critical time in history today. There are strong interests in smaller, simpler, more efficient and cheaper nuclear power units for generating electricity and processing heat, reactors that will require considerably less footprint to erect and operate. To make the smaller units competitive with the existing natural gas, solar and wind technologies, and new manufacturing and fabrication technologies are needed. Figure in this slide provides a broad overview of advanced manufacturing technologies that are currently being developed or assessed by nuclear industry. These technologies include powder metallurgy in connection with hot isostatic pressing, metal additive manufacturing, mainly laser-based powder bed fusion process, a variety of new welding and cladding technologies, for example, electron beam welding, laser welding, cold spray, and diode laser welding. Electric Power Research Institution in US and the Nuclear Advanced Manufacturing Research Center, Nuclear MRC, with several other industrial partners, have been investigating new manufacturing and fabrication technologies for several years. In DOE-funded project, they are seeking to demonstrate that critical sections of a small modular reactor can be manufactured and fabricated in less than 12 months and an overall cost savings of more than 40% versus today's technologies. Upper and lower assemblies of the new scale power reactor vessel are being produced at 2/3 scale using powder metallurgy, hot isostatic pressed and forged components that are then welded together with electron beam welding, a clad with using diode laser cladding. In Europe, Rolls-Royce is now testing the use of new manufacturing technologies, mainly hot isostatic pressing and electron beam welding, for serial production of small modular reactors. The main objective of their FAST project is transition to additive rather than subtractive nuclear vessel manufacturing processes to reduce vessel production cost and lead times. In this part of my speech, I will talk about the technology for production of thick-walled components from metal powder, which is consolidated by isostatic hot pressing. With this technology, it is possible to produce very near net shape components and very complex components, which allows to reduce the overall machining time and material cost. This technology is ideal for manufacturing components that have multiple penetration, such as, for example, the reactor heads. It also produces very homogeneous microstructures, has excellent inspection characteristics, and in some cases you can actually eliminate welds. There are many ways how to use hot isostatic pressing. The most common ones are the densification of products. With this, you densify castings or 3D printed parts or parts that were produced from metal injected molding. Another way of using HIP is to consolidate powder, which is called PMD HIP, where metal powder is consolidated in a canister or mold to solid piece. In this way, you can design a part with near net shape. Diffusion bonding is the third way how to use hipping, which creates seamless diffusion bonds of similar or dissimilar materials with different melting temperatures. What is hot isostatic pressing or hip. The definition of the process is to apply a pressure distinctly higher than the yield strength of material at the hip temperature. So we have high pressure and high temperature, and at this elevated temperature, the yield strength of the material will be very low. And we all know if we apply a stress higher than the yield strength to a material, it will drastically deform. There is an example showing what the hipping can do. In the left picture here, we have two steel rods that have drilled holes in the ends. We put these ends together and weld it, and we created slightly bigger cylinder with a big void inside. These specimens were hipped, and we can see the results in the right picture. There are cross sections. And the left specimen, we can see here, that's the reference that has not been hipped. We can see the big void there, or the big vacancy. The specimen to the right here was an identical specimen, but it was hipped and then cut up, and we can see the big void was eliminated. Hipping will also eliminate internal defects. Any surface-connected porosity or any surface-connected feature will not be eliminated by the hip process, since the pressure medium can penetrate this feature. The shrinkage in the process corresponds to the amount of densification we have. So, for example, if we have material with 2% porosity in the part, and we hip it to 100% density, we will get the 2% shrinkage by volume. If the porosity is homogeneously distributed in the material, the shrinkage will be homogeneous all over the part. The hip furnace can be made for several different materials for different temperatures range, for temperature up to 2000 degrees Celsius and pressures up to 2000 bar. The density of argon at this high pressure and high temperature is very close to water. The densification process is a combination of plastic deformation, creep, and diffusion. Isostatic pressure means that the same pressure is acting on all component surfaces in all directions, and it is achieved by gas pressure medium. The production process HIP begins with the procurement of steel powder used for the manufacture of nuclear reactor pressure vessel, for example, steel 508. For filling the mold canister is needed the metal powder, atomized at gas, with spherical morphology and in very wide particle size distribution. Then we have to encapsulate this powder, so this is based on creating a mold. When the mold has been created, we can essentially fill the powder into the mold. After that, we need to remove the atmosphere. After that, we need to remove the atmosphere via some degassing process, either cold degassing or hot outgassing. When we have the powder in the vacuum in the mold, then it is ready for the HIP consolidation. In case of steel 508 at temperatures in the region 1160 degrees Celsius and argon pressure of around 100 megapascal MPa. This is followed by heat treatment. The last operation is the removal of the canister. This is done either by pickling or machining. In this picture, you can see one half of the lower head of the NuScale reactor produced at 2/3 scale using powder metallurgy, hot isostatic pressing. Also, in the next picture, there are some Rolls-Royce small vessel demonstrator made by hot isostatic pressing technology. The other very important technology for production components for energy for nuclear industry is electron beam welding. Electron beam welding is a joining process that is commonly performed under high vacuum, approximately 10 to -4 torr, in suitable chamber. The chamber prevents scattering of the electron beam during the welding and shields the high energy X-rays emitted during the process. The process employs a beam of high-energy electrons between two materials, workpieces that are closely fit together and in contact with one another to join the materials. The electron beam causes the material on either side to join to melt, and the resultant vapor pressure of gaseous metal generates a keyhole through the full thickness of the joint. The keyhole is advanced along the joint seam as the weld is being performed and closes just behind the weld front, as shown in figure. Electron beam welding process is extremely efficient, and welding time can be reduced 100 times over conventional thick section welding processes. Post-heated treatment effectively recovers the properties in the fusion zone as well as heat-affected zone. Heat treatment provides properties similar to the base metal properties while eliminating the visual evidence of the weld. Research in the nuclear MRC welding vacuum chamber has demonstrated that electron beam welding can provide an acceptable joining method for reactor pressure vessel materials, both forged and produced by powder metallurgy. Conceptual design of the device for welding the NuScale power reactor pressure vessel is on this picture. The design uses individual modules that can be stacked and destacked to form the vacuum chamber, wherein various sections of the small modular reactor vessel or other component will be assembled via electron beam welding. In the picture, there are some data about current capabilities in the field of electron beam welding at the nuclear MRC. They have a relatively huge vacuum chamber with volume 208 cubic meters. They can handle pieces with weight up to 100 tons. And they use 40 kilowatt electron gun. In this picture, you see welded lower assemblies for the NuScale power reactor vessel with welded joints flange to shell and shell to dome head. Now, several words about metal additive manufacturing. Additive manufacturing is the process of manufacturing of solid object of any complex shape using a digital model as a guide to add layers of material. Additive manufacturing today represents a range of new manufacturing technologies that have already found application in many industries. One of these technologies is 3D printing. The Electric Power Research Institute issued technical roadmap for the implementation of additive manufacturing of metallic materials in the nuclear industry under the Advanced Nuclear Technology Program. For 3D printing of metal components, powder bed fusion and direct energy deposition technologies are at the most advanced stage of the development now. Powder bed fusion is an additive manufacturing process in which thermal energy selectively fuses areas of the powder bed. Technology advantages are ability to create complex geometries that cannot be produced by conventional manufacturing methods, ability to produce functionally graded materials to which the chemistry or structure changes gradually changes as function as position. Technology deficiencies process are limited by size, which limits the size of part to approximately 35 kilograms. The deposition rate is relatively low, approximately 0.2 to 1.4 kilograms per hour. Assemblies may contain cavities, entrapped powder or fusion defects, and in DT inspection of thicker parts and complex geometries can be a problem. This technology is expected to be primarily suitable for fabrication of reactor vessel core components, such as fuel assemblies, springs, instruments, brackets, and so on. The picture shows examples of prints that have been used in the nuclear industry. Another additive technology is directed energy deposition, which is additive manufacturing process in which concentrated thermal energy is directed to melt deposited materials. The process consists of depositing individual layers of powder produced by gas atomization process with thickness of approximately 0.25 millimeters. Advantages of this technology are higher deposition rate, allows the production of larger components with mass up to 250 kilograms. Mechanical properties of such components, such as tensile, impact work, and hardness have been shown to meet or exceed the properties of the same type of material forged. Technology shortcomings. One limitation of the directed energy deposition process is that can usually be used in welding position, horizontal from above, and the potential to create unwanted defects is similar to welding. And directed energy deposition will be primarily used to produce parts such as valves or fittings of appropriate size, as well as control rod actuator parts. In this picture, you will see the process of manufacturing and valve by a laser powder blown that technology from steel 316L. And the last technology I would like to say something about is diode laser cladding. Laser cladding is deposit overlay technology which uses high power industrial laser to melt or weld material into substrate, creating an overlay with true metallurgical bonding. Laser cladding is a very competitive alternative to traditional arc-based cladding methods. Due to much lower heat input, the technology can be used for cladding large surface areas, can also be expanded to applications like repair or additive manufacturing. Almost all types of laser can be used for cladding, but diode laser offer many advantages thanks to their relatively low cost of purchase and operation. The main potential advantages of diode laser cladding are it can be used out of position. Conventional cladding is performed in the downhand horizontal position only. Significantly smaller amounts of cladding powder are required, which could lead to substantial cost savings over conventional processes. And weld dilution is substantially reduced over conventional welding methods, resulting in a much smaller heat-affected region. The potential cost savings from this technology is substantial, assuming that the thickness of cladding can be reduced by over 1/2 compared to conventional cladding methods. For NuScale power reactor, which is clad over both the inner and outer surfaces, the amount of cladding surface area is projected at almost the surface area of 2 Olympic-sized swimming pools. The nuclear MRC operates a 15 kilowatt laser line fiber coupled diode laser controlled by a large gently mounted robot manipulator within 10 by 10 by 5 meter, safely and for sure. In the next picture, you can see process laser heads and nozzles used in developing cladding procedures for a reactor vessel based on NuScale small modular reactor design. The cladding procedure are being developed using 3 welding orientation position as described at ASME section 9. These are 1G flat, 2G horizontal up, and 3G vertical. In the picture you can see deposited layers of austenitic steel 308L on the base material. The application parameters of the corrosion-resistant coating vary with respect to the inclination of the surface to be treated. So every surface are done under different condition. And this is the last slide, which shows that all internal surfaces of the mock-up lower head assembly have been successfully clad with total laser time 18 hours, total process time 21 hours, total powder usage 91 kilograms. The total powder usage was roughly 3 or 4 times less than one would see for a conventionally clad component using submerged arc welding. I thank you for your attention.
I thank very much to Josef for a very nice overview of advanced manufacturing techniques focused on additive manufacturing. For me, it was very interesting overview. It seems that we will be able to see completely printed nuclear reactor soon, yes, including fuel assembly. Okay, are there any questions? Yeah, I see the audience is today's silent day. Okay, I would like to ask maybe one thing. What would be your preferable technique from what you were presenting? I mean, what you think it's the closest to application and.
I think that reasonable would be to start doing hipping.
Hipping, okay.
Because 3D printing is technology on every street now, every laboratory. But hipping in the Czech Republic, no.
Mm-hmm. Okay, thank you very much. There is one question. Okay, great.
So, thank you for your speech. And my question concerns the hot isostatic pressing and the design of new scale reactor. So, am I true that it looks that it should be some important technology for a new scale reactor?
What I show, it was some mock-up in some small dimension, and the main problem nowadays is to have a large furnace. It's a key problem, this technology. But I think that some years we will see that it's very expensive. So I don't expect that we have some big furnaces in Czech Republic, but in some bigger countries, such as US, I think that they will go this way.
Okay, thank you, Josef. Thank you. And we can move on to the next presentation, which is dealing with the laser shock cleaning technology that will be presented by our colleague, Zbigniew Spirit.
Good afternoon, ladies, gentlemen, and everybody. I would like to introduce me. I'm Zbigniew Spirit, and I'm from the Department of Material Testing. And I prepare a short presentation about LSP technology, and I would like to focus on experience with this technology which we have in CVR. Okay, for introduction, I would like show partners with LSP technology, because we haven't got LSP technology now, but we want to buy it in maybe next years. The mainly partner is Institute Highlights from Dolní Břežany. The building is on the right. Which we collaborate 6 years. And the second partner is Laboratory of Laser Shock Processing for Advanced Material in Technical University in Cincinnati. We collaborate with Professor Manava or Professor Vazudanev. It is a guru of the LSP technology and application of this technology for industry. And mechanical testing and corrosion testing, which we present here, were performed in mechanical testing laboratory in building G2 in Pilsen, in a remote workplace of CVR. Okay. There is a short history about LSP technology. The first message from pulse laser interaction with metal surface is from 1962. Askarin and Morrow set out to measure the photon pressure of laser pulse on a metal surface in Lebedev Physics Institute in Russia. Then were performed the first test of LSP treatment specimen, tensile test on alloy. Aluminium alone 7075. Then in 1980, first LSP treatment on steel on 4340. It was performed a fatigue test with very good results. The fatigue life increase. And very important data is 1990. It was first industry application for US Air Force on engine for F101 for first stage of fan blades, the engine. Because this engine had a problem with on the B-1B bombers were vulnerable to foreign object damage on the leading edge, and the damaged blades could fail in a flight and destroyed the whole engine. It was a very big problem because the services of these engines was very often, and it was very expensive. Therefore, in 1996, were performed a lot of fatigue tests on base material from the blades. As you can see at the chart, on the base material and with EDM artificial notch, and on the base material with notch, and on the material after treatment classical shock peening, so you can see in the middle, and with the LSP technology, LSP peening, laser shock peening. And as you can see, the fatigue results were excellent for LSP. The fatigue life of heavily damaged blades with LSP was the same as the new blades. It's a quite good result. And from 2003, the LSP technology begins production LSP blades on the integrally blade rotor for the next generation engine of airplane. The second important application, industrial application, was in 1999 in Japan, when Toshiba used the LSP to periodically service critical components on the reactor vessel. The reason for this was to increase the resistance of components and welds to stress corrosion cracking that occurs in these types of reactor. This method improve resistance of stress corrosion cracking in critical area, like welded joint, H1 and H2 and so on, in a nuclear vessel. The guru and of this technology for nuclear vessel is Professor Vijay Sano. And the method substitute a tensile stress, which is after the weld, compressive residual stress by LSP. Okay. And I would like say a few information about LSP technology. LSP, laser shock peening technology, or laser peening, it's very similar. LSP basically achieves similar effects as conventional shock peening treatments existing in the industry for over 6 decades. In traditional shock peening process, metallic, ceramic, and glass balls, acting a minuscule ball peen hammers, make a small indentation on the metal surface and impact. Unlike a conventional surface hardening, LSP introduced a pressure residual stress at higher depths. It's very important. And the hardening process is full automated. Each pulse is full definited. It's not a random process. We can do very good simulate the process and better set up the process for the hardening. On the right is the table with 4 peening methods: laser peening, shock peening, ultrasonic peening, and water jet peening. And on the right is maximum depth of applied compressive stress for steels. You can see the laser shock peening has 10 times more depth comparing with shock peening. And the maximum residual stress is higher than shock peening. And unfortunately, the LSP effects prolong the fatigue lifetime. It's a very similar with classical shock peening, as you know. Okay, and about a few information about principle of LSP. The principle of LSP is based on a conversion laser energy into shock wave that results in material plastic deformation and a redistribution of the residual stress. There are 3 steps of the process. In the first steps is metallic surface with a sacrificial layer, obviously like black paint or tape, or without tape when we use the method under the water, and a plasma confinement layer, obviously water or can be a glass. Then the laser beam pulse is focused onto the sample, and laser beam passes through the confinement layer and absorb in the sacrificial layer. Only in sacrificial layer it's important, no in a surface of metallic treatment. Then, after the interaction, the plasma is created and rapidly expands, creating extreme pressure. The pressure must be higher than a dynamic yield strength of treatment material. It's important. And then the confinement layer increase the pressure even more. It's like shield. Then the pressure causes the plastic deformation of the part, introducing the compressive residual stress into the surface layer, and we have better fatigue properties and higher hardness and so on. Okay, there is a short example how the process is like. There is from laboratory of highlights in Visioning, and you can hear the process a little bit noisy, like the machine gun fire. As there is a simple strategy of shooting next by the next shot. Okay. There is another example how the surface can look like after and before and after LSP. On the left is surface after turning, and the right is surface after LSP. The information is the surface and the roughness can be better previous the treatment. When we use a good overlap, good setup of LSP process, the roughness it's not a problem with this with the treatment. Okay, now there is a list on the of the mechanical properties which could we improve and increase. Increase the static mechanical properties, extending fatigue life, increase resistance of stress corrosion cracking, and a method for extending fatigue life of turbine blade affected by pitting corrosion. Their properties is very important for material for power plants or nuclear power plants and in energy sector. Okay, we used two-based material, experimental material. The first one is austenitic stainless steel, Ghost 08 CH18N1010. Austenitic steels stabilized by titanium with certification 3.1. It's a certification for application in nuclear power plants. Austenitic steels is for nuclear power plants based on Russian design. It's a classical material for primary circle. There is a chemical compositions, and there is mechanical properties. The yield strength is 250 megapascals, and ultimate tensile strength approximately 565 megapascals. And relative big elongation, approximately 55%. The second material was martensitic stainless steel, which is used for highly stressed turbine blade with good creep resistance, corrosion resistance, hardened and tempered steel, with good toughness and good creep rupture strength. And the mechanical properties of the material is yield strength 760 megapascals and ultimate tensile strength 1100 megapascals. Okay, we used two technology and two LSP station for our experiment. The first and mainly is LSP station in highways with L2 bivoy laser system. With wavelength 1030 nanometers, pulse rate 10 nanometers, maximum pulse energy 100 joules. It's a very powerful laser with a frequency of 10 Hz. And the second LSP station and LSP system is Continuum at the Cincinnati Technical University, a Center for Laser Shock Processing for Advanced Materials and Devices. The properties of LSP station is similar, but the maximum pulse and energy is only 5 joule. But it's not a problem for LSP application. Okay. Setup for LSP treatment. It's very important when we applying LSP technology. It's always important to set up a process well for the material, sample or component. Shortly, when we use the LSP for some materials or component, we must know where is the critical area, where is mechanisms of degradation, is fatigue or it's a stress corrosion cracking, where is the problem, where is the location with maximum stress, and we must know where maximum information about behavior of the material and properties, how the component loading and so on. Then we can modification LSP parameters for the application. The base parameters, LSP parameters are energy, impulse, pulse height, power density, overlap, layering, and shot strategy. On the slide you can see some strategy. The first strategy is for large area. It's a simple, it's good for increase the hardness of surface. And strategy for surface with notch, we used a special strategy with a lot of pulse. You can see in the center. When the goal of the strategy is redistribution maximum residual stress, compressive residual stress, it's to one point or small area. Or we can use only one or three shots for the notch. You can see on the right. Okay, there are some results from tensile test on two experimental materials. There is results before treatment, LSP treatment, and after treatment. You can see the yield strength on austenitic steels increase from 277 up to 481. And similar effect is with ultimate tensile strength, but in the second material, martensitic stainless steel, the effect of LSP treatment was very little, and the value of yield strength and ultimate tensile strength before and after is minimum, and the value is very similar. Okay, there's a result of analysis of residual stress measuring on specimen for the 3-point bending test, fatigue test. And the goal of peening strategy was to move the maximum compressive stress to critical area just below the notch, area 1. The area 1 is nearby the notch, where the maximum tensile stress for high cycle fatigue, and to suppress the correct initiation and propagation. The other area 2 and 3 is farther than the notch. And as you can see on the chart of average value of residual stress in each area, you can see the maximum residual stress, compressive residual stress was measured in area 1. And previous value was approximately 180 megapascal, and after treatment was 420 megapascals. In other area, the change was very little and no important, because the most important was the condition in area 1. Okay, there is a result from fatigue test of same specimen, and you can see the fatigue strength increase from 180 up to 280. There is a picture of specimens after peening of austenitic steels. The material was austenitic steels. Okay. And there is shortly results of stress corrosion cracking test according the standards ASTM G36. The environment was boiling magnesium chloride solution, and the specimen was manufactured from pipe from austenitic steels, and the maximum tensile stress was up to yield strength approximately 215 megapascals. Then the specimen treatment and no treatment specimen were exposed 20 hours in this environment, and then we made metallographic analysis in light microscope and scanning electron microscope. On the center is the results. You can see in the area with maximum tensile strength here, was observed many cracks with depth approximately half millimeters. And on a treatment specimen, we didn't see any cracks. It was a very simple test, but I think the results it's okay and fine. Okay, and on this slide is possibly possible LSP application in power plants. The first one is a method for extending a fatigue life of turbine blade affected by pitting corrosion. The last blades on the turbine for classical power plants, like coal power plants, has sometimes problem with pitting corrosion. You can see there, and the pitting corrosion is like a notch in the material and in the blade, and when we the pit is in the shape and the biggest of the pits is so much, it can be problem from this place can be initiation and crack and can be damage all blades. It's a problem. The second is extension of service life of the heterogeneous welded joint on the secondary circuit of nuclear power plant by suppressing the mechanisms of corrosion cracking by applying compressive stress to the root of the weld. There is a problem with stress corrosion cracking between heat affected zone carbon steel and weld. And from the root can initiation a crack and then propagation along the interface. Okay, and when we try and we tried treatment the root of the weld and applied compressive residual stress for this area, from this area, in this area initiation, crack and then propagation. There is first results from measure of residual stress before and after treatment by hole drilling. And the most important chart is in the center. As you can see, the orange curve is before LSP, base material, and blue curve is after LSP. And as you can see, the compressive residual stress increase from 0 or 50 megapascals up to 450 megapascals. And the compressive residual stress was measured up to 1 millimeters. What is interesting is a behavior out of the LSP treatment area. For example, this chart. You can see the residual stress was before treatment, orange, and after treatment, blue. As you can see, from the small compressive residual stress, the residual stress transformation to tensile stress. It's a good example how the LSP redistribution residual stress from compressive residual stress on tensile residual stress from this area which we treatment to out of the area. And it's okay because it is not a danger area, and from the point the crack initiation, no initiation. Okay, and the last results of experiment of high cycle fatigue on material for turbine blade on BLR T552. Efforts of LSP technology to suppress the notch effect of corrosion pits of steam blades is the goal of the LSP treatment. The issue of corrosion pits on blades, especially of low pressure stage, has been solved for several decades. It's no problem. And the parameters of experiment are based on research reports and expert articles for reloading of the blades of L-1 steam turbine 110 megawatts. The notch The artificial notch was made by laser drilling. The diameter of notch was 250 microns and the depth was 500 microns. And there is a specimen. We used pinning strategy. We use only three shots, as you can see on the animation. And the pinning area was 4 × 2 millimeters with 3 spots. And the goal of pinning was redistribution maximum compressive residual stress to nearby the notch in this, because we know how the crack initiation and how propagation. There is only example how the notch looks like before LSP and after LSP. On the left is base material with a notch. Without LSP, in the middle is first LSP modification with 1 layer, and on the right is LSP with 3 layering pinning. On the right, the top right, is corrosion cells which we used for mechanical testing and corrosive environment up to 100 degrees Celsius. Okay, and there are results from high cycle fatigue test in SN curves. The curve 1 is samples without defect, with polished surface. The fatigue strength was evaluated 380 megapascals. Then we perform a test with the same sample but with artificial pitting with a notch. It's the curve 4 and it's down, and the fatigue strength decrease up to 80 megapascals. And between is 2 and 3 curves number, and you can see the fatigue strength increase from 80 megapascals up to 300 megapascals. On the right, there is tests at room temperature and air condition, and on the right this is from a steam condensate at 100 degrees Celsius. And the point, like star, is between fatigue strength with pitting notch from test at air and room temperature, and on the top is fatigue strength without notch at room temperature and air. And last information. We perform on all specimen fractographic analysis, and what is interesting from fracture analysis is based on fractographic analysis, it can be said that the fracture mechanisms of recognition is in the same in all series, without LSP and with LSP, and with notch and without notch. However, the minor difference is the priority direction of crack propagation. It's different. As you can see on the first and second picture, the crack propagation along the surface. But in LSP treatment specimen, the priority direction was in radial direction. The reason for crack propagation in radial direction is the applied compressive stress on the specimen surface near the notch, which block the crack propagation along the specimen surface. Crack propagation in radial direction is slower because the condition for crack propagation in radial direction is more energy demanding. Yes? And summary. There are some results from mechanical test. And for results, I can say, based on the present results, it can be said that LSP technology can improve especially fatigue properties, suppress the effect of notch fatigue behavior in the material or component material, and increase the resistance of material to stress corrosion cracking. Okay, thank you for attention, and that's all.
I thank Zbigniew for his presentation. Obvious question, do you have any question to what you hear, what you heard just now? Presentation of today, after so many interesting information related to material research, methods, corrosion, even advanced manufacturing, you will hear like something about material degradation, and this is specifically material research for the high temperature gas-cooled reactor applications. So, and since you stayed here until now, so you see that there is already organized some show. We are three for you. I will shortly introduce the topic, say a few words about the fuel cladding materials, and then my colleague Jan Becker, who is actually the expert and the one who is doing the research on high temperature materials for HDR GFR technology from beginning of CVR, and our young colleague, actually I heard today that it's going to be our colleague, it is our colleague, new one, continuing the material research. So let's proceed. You will see a few words about the motivation, why, what are the HTGR reactors, high temperature gas reactors, then some projects which are related to the helium technology, experimental facilities, and results, of course, of different type of material for those type of reactors. So you may know you are all highly educated in the advanced nuclear reactors. This is one of the 6 concepts of the advanced generation 4 reactor. One of them is high temperature gas-cooled reactor, which is on slow neutrons, thermal neutrons, and this is all the technology already been tested and proved in Germany. And recently there is HDR reactor actually working and supplying the grid with electricity in China. It's 210 megawatt power. Maximum temperature of outlet temperature is around 750 degrees centigrade. There is the cycle that goes directly, not directly, but to the steam generator. So the steam is produced, and as I said, electricity. It's a thermal reactor based on trisofuel particles. The similar technologies in Japan. It's somewhat smaller reactor. It was more for testing and for showing or for employing the actually further cogeneration. You could hear that, of course, since the HDR or the high temperature reactor have the possibility not only of the electricity production, but also there is a lot of waste heat or waste heat that can be used, high temperature heat, and the HDR is in Japan is actually using it for production of hydrogen with the iodine sulfur cycle. I will not go to the specification. It's also of particle graphite reactor, and that technology the world is going farther. Already Chinese are thinking about the HDR PM600, sort of using the HDR PM what they have now for putting more modules together, having even bigger facility. There is also US company X Energy who are actually developing this technology. They have already licensed the fuel line, production fuel line, and in Europe there is the nuclear cogeneration group led by Poland, who are thinking to actually start directly from zero nuclear power to HDR technology next to Schwerk, the research reactor. So we shall see what will be next. So then there is also a fast spectrum gas-cooled reactor. There is you can't see yet any example, and I would say that it is still a long way for the application, because there are many challenges, not only material challenges, but safety, of course, and fuel cladding. Nevertheless, the group of Visegrad countries, together with France, is working on Allegro demonstrator. It shall be 75 megawatt thermal power with maximum temperature 850 degrees centigrade. All those reactors are, of course, with helium cooled, high pressure 7 megapascal. So you can see the Allegro on the left-hand side, how it could look like. Then there is also the parameters in the table. You will have the presentation so you can read it. And there is also very new project of UJV who is going, they are going the direction, I would say, I am calling it personally this PowerPoint small modular reactors. We have done many, which is called HEFAST, which is also a gas fast reactor. But for both type valid that there are a lot of challenges, and I think very important to be solved is the fuel cladding. Since we are expecting the temperature, outlet temperature 850, also for the accident, and not temperature, you have to have material which will withstand much higher temperature, which is currently not. We don't have any of the metallic materials. What is thought and what is developed is the silica carbide composite. There are several companies, including the French CEA. They are attempting to produce. Also Japanese. In this moment, there are still questions in joining and coating. So this is a lovely picture of all the projects which we are having or which we had, which are ongoing, related to high temperature helium technologies, because we have here several experimental facilities devoted to either material research or thermohydraulic and components testing or gas purification. Won't go in details. So, because this is a conference on materials, so devoted materials, so we go to materials which are usually, candidate and selected for this high temperature helium reactors. Since there are many components from the pressure vessel, either HDR or GFR, which can be probably from ferritic, but most probably austenitic steel for GFR, Then we have the secondary circuit that will be must be from nickel-based alloy. In this moment, there is the coded 800H, but also 617 nickel-based alloy. Then we have for several phases candidate material for cladding. It's 1515 titanium. What already Lukáš presented for the for LFR condition. And for the higher temperature, for the phase 2 of the Allegro, where it's expected at 850, then we are researching the ceramic materials. You may know all our facility, but I will just quickly go through. There are several loops where we can study material behavior in flowing condition. Then we have also a static condition in the high temperature furnace. And of course, with all this, we would not do anything without the material characterization laboratories, where is actually the high temperature corrosion described and the mechanisms explained. So for the loops, we have several test sections with different sample holders, design for specific projects, how the time went. So from the corrosion coupons, we were also involved in the project which required the tubular samples simulating the cladding material, and 90 meters per second speed, which is expected in the GFR reactor. So our designers are doing the best to supply us with such a test channel. And these are already results of testing such a material for cladding. It was cladding tube of 1515 titanium steel. Then we had also, for comparison, coated 1515 titanium steel within the GEMA project under the Joint Program Nuclear Materials. The mechanism of the high temperature corrosion is similar. There is the oxidation, even though there is a very low amount of oxygen in the helium, but nevertheless there's always some oxygen or moisture, even in the real condition of the reactor. So this is the driving force for the oxidation, which is actually for metallic materials beneficial. So the chromium oxide layer and spinels are formed on the surface, which are which form homogeneous layer, which is protective. I can't say this the same for the aluminium-based coating, which were produced by IIT Milano. It's the Institute for Technology, Italian Institute, with the pulse laser deposition. Shortly, the coatings are not suitable for the 900 degrees centigrade, and further development, if for this application shall be used, is needed. So there were cracks and they fall off. They were also disintegrating based on composition. And something from the ceramic cladding. You can see here from close by the surface of samples of SIG material. It's produced from silica wafer, which were with CVD deposition sealed with silica carbide. So that's why it's 6-sig. We had samples with different surface roughness, studying if it's if there is some influence of the surface roughness, what is actually the mechanism of the oxidation because for silica carbide in no oxygen or in oxygen how to say, depleted environment, there is the mechanism called active oxidation, which is actually changing the silica into the gas phase and removing from the surface, which is not wanted mechanism. So there is again, for all high temperature materials, beneficial to have some oxygen, and then the reaction goes that the silica oxide is sealing the surface, but not apparently enough. For example, if there were some cracks, because we were using also pre-cracked samples, as you see here, there was no sealing or rehealing of the surface. Maybe I didn't mention, but the silica carbide material composite produced by this way that is in two-step is still not providing completely sealed material. So the idea to have gas tight and mainly transition products like silver tight materials that is not migrating from the fuel out. The tantalum liner was also introduced. But the tantalum liner's problem, if it's uncovered, it suffers with specific oxidation and swelling, and then can, of course, it has different properties, can rupture the silica carbide itself. So after all this study, what we did for the Matisse project, we can say the conclusion that yes, the silica carbide suffers when there is no oxygen in the helium, but there will be always some oxygen. So then it's about of the amount of the oxygen present in the gas, because if there is approximately 24 ppm, then we are suffering with some somewhat higher oxidation rate, and then there is already growing the silica oxide on the surface rather fast for such a time. We were asking here how long it shall stay in the reactor, so this silica cladding at least 6 years, so that it would not be the case for silica oxide grow. So there is a lot to study and to develop. As I said, not only improvement of the surface, composition, sealing, but also joining and coating. So, but since the silica carbide material is also one of the ATF candidate cladding, the development is not going only for the GFR. So maybe there will be one day when it will be in stage that it's possible to use and standardize for the cladding. And that's all from me, and I'm glad to give the floor to Jan, and we will continue.
So thank you, Jana, for very nice introduction and also results. So during the The present project, Thatcher Sodomaher, which was mentioned on the slide, this project, the special nickel-based alloys which are available on the Czech market will be tested. Also, Inconel 617 was included to the testing program. This alloy is regarded to be the best candidate material for components which have to withstand very high temperature. For example, the high heat exchangers and another high temperature components. And also the special ceramics, high temperature ceramics, will be tested within the new, relatively new project Thatcher. So this is some theory from literature, what happened with materials in high temperature helium. Everyone knows that helium is inert gas, it doesn't react with anything, but the helium coolant contains some typical impurities. And the mechanism of corrosion is carbonization, decarbonization, or oxidation. It depends on the partial pressure ratio of these impurities. Below the critical temperature, which is around 900 degrees centigrade, in condition with good ratio of partial pressure of these impurities, the compact and protective oxide layer can be formed. Above the critical temperature, the protective layer is unstable, so the continuous carbonization or decarbonization takes place. So this is a great theory, and now some tasting of results from the finished project. So one of the first tested alloy was the welded alloy 800H within the Archer project, the samples containing the weld joint filled with nitrofer, and the alloy was exposed both in the furnace and high temperature helium loop. Yes, these are the same pictures of exposed samples in the furnace. The surface layer was relatively compact and homogeneous, but in the heat affected zone, the spalling was observed, spalling of the surface layer. So on the cross-section of the samples, weld metal, heat affected zone, and base metal, the compact surface layer made of chromium oxides was observed, and under this layer the corrosion attack along the grain boundaries was found. Yes, the samples exposed in helium loop, the corrosion was similar to that observed from the surface, also including the spalling on heat affected zone. So this slide summarizes the results of testing the materials. Very good corrosion resistance showed austenitic steels even at higher temperature, but the mechanical properties of these alloys are not good at such high temperature. Also very good corrosion resistant since shows iron and aluminum alloys. The local corrosion goes to relatively too deep to the material was observed on casting Inconel alloys. So what we also tested was the effect of recycling alloys content on alloys properties. It was with cooperation with a casting company. What was the goal of this investigation? During the production of high temperature component by precise casting, relatively huge amount of waste alloy is produced. This waste alloy is returned back to production and blended with virgin materials. And the question was if the revert material influence the quality and mechanical properties of the alloy. As received samples and also the exposed samples was tested and some differences was recorded. The conclusion of this investigation was that for stable revert materials influence the quality of the cast alloy, and for stable production quality the ratio at least 20% of virgin material must be maintained. More details you can read in the paper which was published with Daniela. So, within the project we tested also the mechanical properties of selected ceramics materials based on corundum or mullite. The ceramic material were exposed in different environment, among the others in high temperature helium. In some materials, some differences in bending strength was observed, exposure. But the differences were not significant. So we tested not only the mechanical properties of ceramic materials, but also the electrical and insulation properties. What was the goal of this investigation? As you know, the electrical resistance of ceramic material decreases with increasing temperature. So the corrugated ceramics, which we previously used as insulating materials for heating elements of our experimental devices, is not sufficient for such high temperature as 900 degrees centigrade. So we looked for the new materials, and we find out that the electric resistance of corundum is much better than those of corrugated. So we developed the new insulating elements from corundum, which is used in high temperature helium loop. Some new results within the Sodomahe project. This result was attained with cooperation with Terka during our together work on her diploma thesis. I am glad that Terka is here. today with us. Terka, are you looking forward to work again in Severež next week?
Yeah, I look forward next Tuesday to start working here. Yeah.
Hey, I'm glad. And can you tell us some few sentences about your diploma thesis?
Yeah, sure. Hello, my name is Tereza Bartíková, and I would like to present a small part of my diploma thesis focused on material degradation in high temperature helium and carbon dioxide gas environment. Dr. Berka was the supervisor of my diploma thesis, and all the measurements were performed here in a research center, Řeš. And we tested Inconel 617 in coolant simulating gas fast reactors. On the table on the right, you can see the impurities, concentration, and tertiary pressure. And on the left, you can see mass gain during exposure. Also, I'm very grateful to Jan Procházka, who spent dozens of hours with us analyzing oxide layers. Here we have results after 1,000 hours exposure at 900 Celsius. On the first image of SEM of surface, we found pretty nice compact corrosion layer. It contained mainly chromium and oxygen, and small amount of titanium and manganese. On the second and third cross-section image, surface layer is formed from chromium oxide, and oxidation under surface layer is formed from aluminum oxide. And I would like to mention that the test continues up to 3,000 hours of exposure. And it's yours again.
So, thank you, Terka, for a short introduction to your diploma thesis. The test will continue. We will see the new results after the longer exposure. So, when I was working on this presentation, I got the idea to compare the results of high temperature corrosion of Inconel 700, 3 and 8 obtained during the finished project, and hot corrosion of 617. As I said, the corrosion of 700 3 and 8 alloys was only local. Compared to 617, on which the compact layer was formed, and also the mass gain of Inconel 617 was about three times higher than that of Inconel of 703 and 8. But we will see of the next results, because the Inconel 700, 3 and 8 was also included a new experimental program. But so last but not least, the new data about the bending strength changing of new ceramic materials exposed in hot helium, and for comparison also in hot high nitrogen, was obtained and also published. Also in this case, the differences were relatively negligible. So, what's to say in conclusion? As we said, CBRS is involved in projects related to materials for high temperature helium technologies, and within this research program we cooperate with universities and also industrial and research organizations. So the results are not only the data about the corrosion of materials, for example, sand pictures and graphs and so on, but also the results of applied research as prototypes, utility and industrial designs. The program continues. Just for your information, the helium loop is now in operation, so the new samples for Terka are expected. Let me mention that another program is aimed to technologies itself for gas-cooled reactors, and there are also some important or nice results, but that's another story. So I would like to thank you for your attention and also thank my colleagues from CV Press, UJV and University for cooperation. So that's all.
So thanks to Jan and Reza. Again, questions. So, do you have any question to our last presentation or to any presentation before? Because we still have speakers here from the time after lunch. So you didn't surprise me. So okay, thank you very much for staying until now. Thanks again to presenters, all presenters, and I would say we will conclude this event. And yeah, let's see next year what will be the topic. So thank you very much.